Hello everyone, welcome to lecture on digital logic design. I'm Dr. Vilayat Khan. In this lecture, I will talk about binary counters. Binary counters are sequential circuits that changes its states between different binary sequences. The binary sequence can be a sequence in ascending order, or it can be a sequence in descending order, or even the values can be random. So depending on the applications, different types or different kind of binary counters can be designed using sequential logic. Counters are very important circuits used in different digital logic circuits in digital systems. For example, they may be used to count numbers in different ways. So they are very important circuits of digital digital components. In this lecture, I will explain how we can design a 3-bit binary counter. A 3-bit binary counter counts from 0 to 7 decimal numbers. And as it is a 3-bit binary counter, we represent each number in 3 bits, 3 binary digits. Here on the screen, you can see a state diagram that shows the transition from one state to the other, and then from the other to the other, and then it repeats. So let's assume the binary counter begins at 0, 0, 0, and the arrow shows the direction of the transition. The next state 0, 0, 0 represent the decimal digit 0, and then the next state is 0, 0, 1, which is the digit 1, and then it counts to digit 2, which is represented in binary as 0, 1, 0. Then from 0, 1, 0, it moves to the next state, which is 0, 1, 1. And from 0, 1, 1, it moves to 1, 0, 0, which is 4. And from 1, 0, 0, it moves to 1, 0, 1, which is 5. And from 1, 0, 1, it moves to 1, 1, 0. And from 1, 1, 0, it moves to 1, 1, 1, which is 7. And then it repeats back to the initial state of the sequential circuit. So we have 3 bits, and the values of these 3 bits changes in ascending order from 0 to 7. Each sequence represents 7 digits of the decimal system, 0 to 7, and then it repeats. Here we have the excitation table for the 3-bit binary counter. On the left hand side, we have the sequences that we want to be shown by the circuit. The 3 bits are represented with a 0, a 1, and a 2. And the starting sequence, the starting state is 0, 0, 0, then it moves to 0, 0, 1 until 1, 1, and then it repeats. On the right side, we have the inputs of the flip-flops that would generate when this group of bits are provided at the input of the flip-flops, then it would change the states of the flip-flops in this order, which is the desired order in this particular example. If we look to these bit sequences, every bit either remains the same or it inverts, the value of the bit inverts. For example, here when we move from this state to this one, this bit inverts, and the other 2 bits remains the same. 0 remains the same, 0 remains the same. and this happens, or this is the case in all transitions from one state to the other. So a T flip-flop is the solution for such a circuit. In the T flip-flop, there is a single input T. When a 0 is provided as the input, the current state of the flip-flop doesn't change. But when a 1 is provided at the T input of the T flip-flop, the state inverts. Whatever the value the current state has, the next state is the complement of that current value, the current bit. So we can design or implement such a 3-bit binary counter by using 3 T flip-flops. So let those flip-flops be as 0 or 0, 1, 2, and the T input of the flip-flop 0 is T as 0. The T input of the flip-flop 1 is TA1, and the T input of the flip-flop 2 is TA2. And we get these sequences from the outputs of the 3 flip-flops. The output of the flip-flop 0 is A0. The output of the flip-flop 1 is A1. The output of flip-flop 2 is A2. So these are the outputs of the 3 flip-flops, which is the state of the flip-flop, and that is actually the output of this sequential circuit. And these are the 3 inputs to those 3 flip-flops, so that we can get these states in this particular order. So how can we, given this count sequence, we can create the values in these 3 columns. So let's start with the first one. When we are in this state, this is the current state of the 3 flip-flops, and we want to move to this next state. This is the next state. Then this is possible if we toggle the state of A0, and if we keep the state of A1, if we keep the state of A2. This is 0, so we keep it at 0. This is 0, we keep it at 0. This is 0, and we toggle it. To do this, or to achieve this, we must provide 1 at the T input of flip-flop 0, because that will toggle the current state from 0 to 1. And we provide 0, 0 at the T inputs of flip-flop 1 and 2. So by providing 0 at the T input, A1 and A2 will keep its states. They are at 0, so they will remain at 0. So we will achieve 0, 0, 1, and that is the next state. Similarly, when we are, this arrow represents the current state, when we are at the 0, 0, 1, and we want to come to this state, to move from this state to this state, we have to toggle the state of A0, we have to toggle the state of flip-flop 1, and we have to keep the current state of flip-flop 2. So we provide 1 to the T input of flip-flop 0, 1 at the T input of flip-flop 1, and 0 at the T input of flip-flop 2. So the sequence is 0, 1, 1. That is the input sequence to the 3 flip-flops. When we are at this state and we want to move to this one, the current state is 0, 1, 0, and we want to move to this state. This is possible if we toggle the state of flip-flop 0, we keep the state of the flip-flop 1, we keep the state of flip-flop 2. So we provide 0, 0, and 1. That is 0, 0, 1. When this input is provided to the 3 flip-flops, we will get to this state from this state. Similarly, if we are in this state 0, 1, 1 and we want to come to this state, then we have to toggle the state of flip-flop 0. We have to toggle the state of A1. We have to toggle the state of A2. So we provide 1, 1 at the T input of the 3 flip-flops. So this will enable us to move from this state to this state, or we can say that it will change the current state from here these values to this value. We proceed this way. The current state is 1, 0, 0 and we want to come to 1, 0, 1. So this is the digit 4 in decimal system and this is the digit 5. So we want to show 5 after it has shown 4, and similarly for other digits. So to do this, we have to toggle this state, we have to keep this state, we have to keep this state. So 0, 0, 1, 0, 0, 1 should be the input given to the 3 flip-flops. When we have the current state is 1, 0, 1 is the current state, and we want to go to 1, 1, 0 as the next state, we have to toggle the state of flip-flop 0. We have to toggle the state of flip-flop 1, and we have to unchange the state of flip-flop 2. So 0, 1, 1 should be given as the input to the 3 flip-flops. So 0, 1, 1 is given as the input to the 3 flip-flops. When the current state is 1, 1, 0 and we want to go to next state, which is 1, 1, 1, 1, we move from the current state is 6, but we want the flip-flops to show 7, which is equal to this binary sequence 1, 1, 1. Then we have to toggle the state of flip-flop 0 and we have to unchange the state of flip-flop 1 and 2. So we have to provide 0, 0 and 1, 0, 0, 1. Similarly, we have reached 1, 1, 1, the state 1, 1, 1. Now we want the states to be repeated again from 0, 0, 0. So we have to move current state. When the current state is this one, we would like to move back to the initial state, which is 0, 0, 0. To do that, we have to toggle this state because we want to change it to 0. We want to change the state of this flip-flop to 0. We want to change the state of this flip-flop to 0. So we have to toggle the states of all the 3 flip-flops, and to do that, we have to provide 1, 1, 1 at the T inputs of the 3 flip-flops. So by providing 1, 1, 1 to the 3 T inputs of the 3 flip-flops, it will change or toggle the current state of the flip-flops, which is desired here. So this is the excitation table. The flip-flop inputs, the equations, the columns on the right hand sides are actually the inputs to the flip-flops to achieve these desired count sequences in this order, and they are taken from the outputs of the flip-flops. We have to create simplified Boolean equations for the input of the flip-flops so that we will get the desired input at the 3 T flip-flops to get the desired count sequence. This is the desired count sequence. So you have to create Boolean equations for the T inputs of these 3 flip-flops. Here we have the same excitation table. These are the output columns. Even though they are labeled as flip-flop inputs, but they are in fact the outputs that you would like to create and then connect it to the inputs of the flip-flop. Here is the K-map for the TA2 Boolean variable. This is the function TA2, and it's a 3-variable Boolean function because we have 3 variables here, and these 3 variables are actually the outputs of the T flip-flops, but here they are considered as the input to the inputs of the flip-flop. So this is the 3-variable K-map for TA2, and these are only 2 ones are there. So when we put them on the K-map, minterm 0, which is 0, minterm 1, which is 0, minterm 2, which is 0, and minterm 3, which is 1. And similarly for 4, 5, 6, and 7. The rest of all minterms are 0, and these 2 squares are 1. So when we group them, there is a single 2-square group, and the equation for TA2 would become A1 and A0, so which is written here. TA2 is equal to A1, A0. So this is the Boolean equation for the TA2. Similarly, for the TA1, it's again 3-variable K-map. When we put these values onto the K-map for TA1, we get ones in these 4 squares. So all of these 4 squares are adjacent to each other. So we can create a single group of 4 squares, and A0, which is here, A0 covers all these 4 squares. So the equation, the product term for this group is just A0, and that is the equation for TA1. So TA1 is equal to A0. Remember, these A0, A1, A2 are the outputs of the T flip-flops, but are considered here as the inputs for the toggle inputs of the flip-flops. Next, we have the equation for the K-map for TA0. This is the K-map. All the outputs are 1, so all the squares are 1. And for the 3-variable K-map, when all the squares make a single group, then the equation is written as 1. So TA0, the equation for the TA0 is just 1. So it's logic 1. We will connect this and put to logic 1. So we have achieved or created the 3 Boolean function, simplified form of 3 Boolean function written here. So the equation for TA2 is A0, A1. Equation for TA1 is A0, and the equation for TA0 is 1. So now we can implement these 3 Boolean function to create inputs for the 3 T flip-flops. Here is the implementation. This is a sequential circuit. This is the flip-flop 0, T flip-flop 0. This is the flip-flop 1. This is the flip-flop 2. The Q output of flip-flop 0 is A0. The Q output of flip-flop 1 is A1. And the Q output of flip-flop 2 is A2. So A0, A1, and A2. These 3 outputs are actually the states of the 3 flip-flops, and these 3 outputs or the current state is actually the sequence that we want these 3 flip-flops to show. Similarly, each flip-flop has a T input, and when we generate the inputs as per the Boolean functions created here, we will get the desired binary sequence at these outputs. So the Boolean functions here tells us TA0 is just 1. The T input of the flip-flop 0, which is this one, it is 1. The T input of flip-flop 1, which is TA1, is a 0. So a 0 is taken from here and connected with the T input of the flip-flop 1. Similarly, the T input of flip-flop 2, which is represented as TA2, is equal to a 0 and a 1. So a 0 is taken from here and it is ANDed with a 1, and it is connected with the T input of flip-flop 2. And the pulses, the clock pulses of these three T flip-flops is connected to the clock pulse. So whenever the clock pulse occurs, it changes the current state to the next state according to the excitation table shown before. So this is a 3-bit binary counter that counts in the ascending order starting from 0 until 7, and then it repeats. Binary counters, similar binary counters, can be made for the random binary sequences. They can also be made for the reverse counting. For example, in this 3-bit binary counter, we started from 0 till 7. It counts from 0 to 7 and then it repeats. But it can be done the other way around. For example, starting from 7, then 6, then 5, 4, 3, 2, 1, 0, and then it repeats at 7. This is the excitation table for the 3-bit binary counter that counts in the reverse direction. So again, the count sequence represented with the Boolean variable A0, A1, and A2. And this is the sequence 1, 1, 1, which is digit 7, then 6, 5, 4 until 0, and then it should repeat. Now what should be the sequence of inputs at the 3 flip-flops so that we get this binary count sequence? We can create the values in these columns the same way as we did for the 3-bit binary counter in the forward direction. Let's suppose this is the current state of the 3 T flip-flops, and we want to come to this one. That is, the 3 flip-flops shows the digit 6, 7, and we want to show or move to the next state, and it should show 6, digit 6, and then it show 5, then 4, then 3, then 2, then 1, then 0, and then it should start again. So to do that, to come from this state to this state, we have to toggle or complement the current state of flip-flop 0, and we have to keep the current state of flip-flop 1 and 2. To do that, we have to provide 0, 0, and 1 at the input. 0, 0, 1 at the inputs of the 3 flip-flops. If the current state is this one, and we want to move to this state, we want to go from 6 to 5, then we have to toggle this state. We have to toggle or complement this state. We have to keep the current state of flip-flop 2. So we have to provide 1, 0 at the T input of flip-flop 2. We have to provide 1 at the T input of flip-flop 1. We have to provide 1 at the T input of flip-flop 0. So we have to give 0, 1, 1 to the T inputs of these 3 flip-flops 0, 1, and 2. When we are here and we want to move to this state, this would require to toggle flip-flop 0, to keep flip-flop 1, to keep flip-flop 1. 0, 0, 1 should be the input. 0, 0, 1 is the input. We are here and we want to move to this state. So we have to toggle flip-flop 0. We have to toggle flip-flop 1, we have to toggle flip-flop 2. So all the 3 flip-flops should be toggled. That means we have to provide 1, 1 in the T inputs of the flip-flops. Current state is here, 0, 1, 1, and we want to come here from 3 to 2. We have to toggle this. We have to keep the state. We have to keep the state. That means we have to provide 0, 0, 1. 0, 0, 1 is the input to the 3 flip-flops. We are here and we want to come to this state. We are at the state which shows 2 and we want it to show 1 in the binary. Current state is here and the next state is here. To do that, we have to toggle the state of the flip-flop 0. We have to toggle the state of flip-flop 1 and we have to maintain the state of flip-flop 2. So 0, 1, 1 should be the input. 0, 1, 1 should be the input. Current state is here. Next state is this one. So we have to toggle the state of flip-flop 0. We have to keep the state of flip-flop 1 and we have to keep this state of flip-flop 2. So that would require 0, 0, 1. This one would toggle the state of flip-flop 0 and providing 0 would keep the state of flip-flop 1 and also it would keep the state of the flip-flop 2. And that is the desired. Now when we are here and we want to start again at 1, 1, 1, then we have to toggle the state of flip-flop 0 because we have to convert 0 to 1. We have to toggle the state of flip-flop 1. We have to toggle the state of flip-flop 2, and that would require to provide 1, 1 at these 3 inputs on the flip-flops. So this is the excitation table. We can create Boolean equations for these 3 Boolean variables, and when we map TA2 over to the 3 variable K-map, we get a single 2 square group which is simplified, and we get the product term for this single group, and that is equal to A1 prime, A0 prime. So the Boolean equation TA2 is equal to A1 prime, A0 prime. Similarly, the Boolean equation TA1 can be simplified using K-map, and when we do that, we get 4 squares as 1. When we group them, these 2 squares can be combined with these 2 squares to form a group of 4 squares. And when we get the product term of this single 4 square group, we get A0 prime because A0 is here, A0 is here. So A0 prime is the only literal that covers these 4 squares. So that is the equation, the Boolean equation of TA1. So TA1 is equal to A0 prime. And then finally, the Boolean function TA0 is 1 for all the inputs. That should always be 1. So when it is mapped over to the 3 variable K-map, all the squares are 1. So they can be combined. All the squares can be combined into a single group, and that means we have the Boolean function TA0 is equal to 1. So we have got the 3 Boolean equation TA2, TA1, TA0. These are the 3 Boolean equations that would generate the output which are connected to the 3 inputs of the T3 flip-flops. They are here just like the previous example. This is the T flip-flop 0. This is the T flip-flop 1. This is the T flip-flop 2. And the outputs of the 3 T flip-flops are represented with or designated with A0, A1, and A2. These three outputs are actually the current state of the three flip-flops, and the same values of the three state bits of the three flip-flops can be used to produce the outputs or the input for the three flip-flops according to these three Boolean functions. So TA0, which is the T or toggle input of flip-flop 0, is 1. So the toggle input of the flip-flop 0 is connected to a constant 1, logic 1. Similarly, the T input of flip-flop 1 is TA1, and that is equal to A0 prime. So A0 is complemented and is connected with the T input of flip-flop 1. Similarly, the T input of flip-flop 2 is defined to be A0 prime and A1 prime. We got A0 prime from here, we get A1 prime from here, and we end these two variables A0 prime and A1 prime, and we get the output which is connected with the T input of flip-flop 2. And similarly, the three clock pulse inputs of the three T flip-flops are connected with the count pulse or the clock pulse, and the function of this count pulse is that whenever a pulse comes, the state of these three flip-flops changes according to the sequence defined by the excitation table. Using the same approach, binary counters can be made for the random binary sequences or any other defined order of the binary sequence.